Yeah, so ESG is a group for hardware. So I started this group, I think about 1 year ago. And the idea was to have a kind of meetup group for anyone interested in hardware. And at the time, there didn't exist any group like this. So we have groups about Java programming, there's groups that do Kotlin, groups that do JavaScript and all of that. So I think on Meetup, this is the only group so far, I think, that does hardware. And since then, we've kind of tried to grow the group, trying to do talks, trying to do workshops as well. So we had a Christmas special about vintage gaming. And we're trying to have basically one social every month. So since I'm not Mexican, my wife she's Mexican, but I'm not. So I try to speak Spanish, but it's poquito, poquito. Little bits. I will get there, I'm sure. But so I'm doing my talks in English. I'm trying also for encouraging others to do their talks in English so that we can reach a wider kind of audience. But I mean, I'm not opposed to if you say, I'm already a little bit insecure doing a talk in Spanish, so you don't have to do it in English. So it's perfectly fine. So this is the first social we're going to have of embedded systems this year. So there was supposed to be one last month, which we couldn't do because the speaker and myself didn't feel very well. We were sick. We didn't have one in January because I was traveling. So from now on, I'm hoping to have a social every month so that we can meet and have talks every month. So what are these talks about? So what we want to talk about is everything related to embedded systems and hardware. So this includes microcontrollers, it includes Linux embedded devices, which we're going to have a talk today by Josue. It includes hardware, it includes vintage gaming, retro hardware. So I will give a talk later on about some things related to Atari 2600. And also, I don't know how many of you have been to the Security Hack GDL conference last week or 2 weeks ago. There's one, too, yeah. So there's a growing also community in Guadalajara related to security engineering. So I would also like to do more about security engineering. And this is still not really finalized because we need speakers. And that's where also you come in. If you like to do a talk about some topic, I'm very happy to have speakers. So ideally, to have 1 or 2 speakers every social would be fantastic. And then also I don't have to give a talk myself and bore you. So it would be very nice to have speakers. So just to get an impression, who's here for the first time? 1, 2, oh wow, a lot. Very happy about this. I noticed that some people I talked to on WhatsApp and per email. So I really hope, guys, that you enjoy the talks. I brought some beers. So I don't know, Cynthia, we have somewhere. Yeah, there's some beers in the fridge. Help yourself. Maybe there's only 3 packs, so just have 1 for now. And if some are left, then have some more. And we don't have sponsors at the moment, so we're still looking. We have 1 or 2 companies who are happy to sponsor us. And as soon as we have sponsors, there will be food as well. So no food today. We might go for some snacks afterwards. So if there's a critical mass and like to say, let's have a beer after the social, we can do that. But unfortunately, no pizza and nothing else as well. But I think we're trying to make up for it, having really nice talks. So it's an open group. We are all, well, you might be experts, I'm not. But I think there's a lot of people here who are coming out of curiosity, who want to learn about hardware. And there's no expectation that you need to know about a lot of these things. So the idea is to give presentations, teaching others about these kind of stuff, learning together about hardware. So don't be afraid if you think, well, I know Java, I do some software engineering, maybe even in C, but I haven't done much hardware. So that's not really a problem. We're all kind of in the same boat. So ESG will continue for the year, I hope. I have a couple of topics, but I'm happy for suggestions. So last year, we talked a lot about Arduinos. So we had 4 or 5 talks, I think 4 talks about Arduinos, about how you interface with them, protocols, how you program them, sort of basic stuff, also some interesting things. And this year, I want to shift this a bit to using different microcontrollers. So we want to use things like maybe ESP32s, want to maybe look at Raspberry Pi Pico, which is a really interesting controller, because these controllers also, they have features that maybe a simple Arduino AVR processor doesn't have. So from a software engineering perspective, they're quite interesting. The other thing, as I said, is security. So we hopefully have a few talks on hardware security, maybe possible ways in which systems can be vulnerable. And in my area of work is actually related to security. So I do work on projects that do target secure devices. So I'm very happy to also share some knowledge there. And otherwise, it's really open. So whatever you like to hear or what you like to talk about, we have a WhatsApp group, and I can maybe share the link with you in case you want to take a picture of that. I think it is on the website, or maybe it is not. I'll do that a bit later when I give my talk, so stay around. And we also have a GitHub page. So the GitHub page is meant to collaborate. So if you have an idea of something you want to develop or share, you can go on this GitHub page. We don't have a lot there, but I'm hoping in the future there will be more collaborations on that. So what's really important is to have a venue like this to do these events. And Cynthia, she's the one who's putting most of the effort into having this place for communities available to organize events, encourage people to meet here. So I'm going to hand over to Cynthia, and also thanks very much to Cynthia for all the effort which makes all this possible.
Thank you, Frank. Can I have the other mic? The ones in your turn.
Oh, yes.
Sorry.
There you go.
We're still making a little bit of testing on the streaming, so we're streaming on YouTube and Hernandez channel. We're trying to, start a community online too, so we're doing some tests. So, voy a hablar en español. Es importante también que Frank recuerde que hay que escuchar el español. Voy a hacer como un poquito la mezcla de los dos. Bienvenidos a Hacker Garage. Hacker Garage es un espacio, makerspace, hackerspace, que básicamente es, digamos, un laboratorio de creación, de producción, pero pues en realidad es un espacio que está aquí para que ustedes y quien sea, anyone can come here and learn about technology. Somos un espacio que le da la bienvenida a cualquier persona que tenga este gusto y estas ganas de compartir el conocimiento de allá para acá y de aquí para allá, ¿no? Siempre como en un sentido social, comunitario. Así que qué bueno que vemos caras nuevas, me emociona, está padre. Toda la información de las cosas que hacemos pueden verlas en nuestras redes o en nuestra página web, que es hackergarage.mx. Nos movemos por membresías, pueden pagar una membresía mensual, venir y usar todo lo que tenemos aquí completamente libre, o pueden pagar un pase del día si quieren venir a hacer home office, usar herramientas, necesitan imprimir algo, cualquier cosa. Así que, pues nada más, muchas gracias, los anuncios ya se los di, baño afuera, haz productos ahí, chelas gratis hasta abajo, y pues nada, bienvenidos, los dejamos con Josue, y adelante. Muchas gracias. ¿Quieres usar el pedestal amarillito? Digo, blanco.
Ah, sería bueno.
Sí. Ponte
Sí.
donde más cerca que se pueda.
Make a bit more space for you.
Ok. ¿Te digo?
Sí.
A brincarlo, ¿no? Pero... Ahí está.
So I'm just going to set up and then start.
Sorry. I was a bit late. Let's see.
Llévala yo.
Okay.
Listo. Vamos a usar los dos micrófonos.
Ok. Give me a minute. Dame un segundo.
Sí, sí, claro. ¿Aquí te lo dejo?
Esto no se ha
Nada más lo tienes que
actualizado.
prender para hablar y ya.
Ok. ¿Y dónde quedaron los speaker notes? Ahí están, listo. Hey, hello? It is off. Okay, hello. My name is Josue Hernandez. I'm part of this embedded system group. And today we are going to explore the Linux driver device, Linux kernel device drivers using the GPIO ports of a Raspberry Pi. Well, sorry, I'm a bit nervous. Who am I? I am, as I mentioned, my name is Josue Hernandez Gutierrez. I'm a software engineer that has been working as a software engineer for around 15 years. One of the main topics that I have been working on is Linux. I started working mainly, I started working as a web developer, just setting up Apache web servers and things like that. And one of my biggest goals was contribute to the kernel to the USB subsystem, decoupling the PCI, codes for the XH extreme host controller interface part. Right now, I'm working in a company named Oracle. I think you have heard about it. I'm working as a package maintainer. It looks like nothing really fancy, but it's okay. I do some code when I need to patch something and things like that. Give me a second. Okay. Well. As part of a big company, there are some kind of things that we have to clarify. People tend to think that if you are part of a company and you are going to present, you are talking on behalf of the company, but that is not the case. And I need to present something like this just for legal reasons, because probably you are not going to sue me if I say something wrong, but probably the company is going to sue me if you get angry. Then I don't want that. Okay. This is basically the agenda. We are going to provide some context about what is a Raspberry Pi, what is GPIO, and what is Linux. This context is just kind of put everyone on track of what we are going to talk about. After that, we are going to try to answer this question. How can we use GPIO pins on a Linux machine? And we are going to explore all these mechanisms and trying to go to the perfect way to do it. Probably not perfect, but yeah, to the better way. What is a Raspberry Pi? The Raspberry Pi boards are a series of, they are called a single board computer, and they are developed in the United Kingdom with the idea of teach students computer science. That was the original goal, but it grows too fast, and now they are doing lots of stuff. Basically, these are the boards. Just don't keep the memories, because I have all the hands off there. These are the boards. There are some of them that are actually computers. Frank?
Cool.
There are some of them that are actually computers, like any computer that you can have. Practically, three of them that are three of the ones of the boards that I'm showing you are the boards that are really computers. The other one is a microcontroller. The Raspberry Pico is actually a microcontroller. And the boards that I'm showing you are the Raspberry Pi 5. That is the latest version. It has 8 gigabytes of RAM. It's pretty strong. And all of them have an ARM Cortex-A. It means that its processor is an application processor, but they have different characteristics. This is one of the boards that I'm showing you. This is the Raspberry Pi 5. It's interesting that this board now have PCI. But yeah, you are going to say, where is the PCI? Actually, this lane here is the PCI. You need a hat in order to connect a M2 SSD or something similar. But yeah, it's interesting how technology is changing and advancing. But for our talk, we are going to talk about, we are going to be using the Raspberry Pi version 3. Basically, these are the characteristics of the version 3. I forgot to say that the Raspberry Pi consortium has an alliance with the Broadcom company, and they commonly produce their processors. Then it's common that you are going to be seeing the Broadcom everywhere when you are working with Raspberry Pi. Actually, this Raspberry Pi 3 has a Cortex-A that is running at 1.4 gigahertz, and 1 giga of RAM is not really too much, but it is a good amount. Have Ethernet, have this wireless, Bluetooth. It has lots of things like the SSD slot where you are going to use to load the operating system. It is powered up by USB, but the USB port with 5 volts. And the important thing for our tag is that they have this extended 4-pin GPIO header, which is a standard in the Raspberry Pi boards. Basically, all the boards have the same pin out for. Okay, sorry, I'm reviewing my note. This is the pin out that we are going to have in our Raspberry Pi. Commonly, we are probably, I don't know of you, but many of us that are in software engineering have been this board being used to be a multimedia system, or I don't know, a cluster of Kubernetes or something like that. They are useful for that, but they have more power also being extended by these GPIO things. You can even do a robot or something like that with them. Okay, the common, the Raspberry Pi have actually 28 dedicated GPIO pins. They have 14 pins, but they have some pins that are dedicated for other purposes, like providing power. They have a pin for provide 3.3 power and 5 volts power. Also, the GPIO ports provide also 3.3 volts. This is something interesting because the Arduino, I think, is providing 5 volts. Then there is a kind of incompatibility between them that could be solved, but it's not as simple as just connect them. Yeah, and basically those pins allow us to extend our board in the way that we want, and that is what we are going to try to do today. Well, I don't know. What is a Raspberry Pi is clear? Is a board? Yeah, okay. Well, what is GPIO? The GPIO stands for General Purpose Input and Output. Basically, they are pins to extend the board or getting signals from another device or another circuit. You can send them in the board commonly in groups. Those groups are called GPIO ports, and the single pins are called GPIO pins. There are four types of GPIO pins. Basically, there are pins. Well, okay, you can set the GPIO pins in 4 modes. One is the output mode. That it means that you are going to be sending information for to another device. The GPIO input mode, that it is the mode when you are going to be getting information. The analog mode, in these 2 modes, you are going to just be sending the maximum voltage or the minimum voltage. Then it is going to mean a 1 or 0. But in the analog mode, you are going to need a digital an analog to digital converter in order to have a range of voltage depending on the information that you are getting. And the last one is the alternate mode. As we saw in the previous slide, there are some GPIO ports that have other purpose, and that is an alternate mode. It means that some of them could be used as an I2C, as a PWM, as a UART or SPI. Okay. Okay, is it clear?
Does the Raspberry Pi have analog mode?
I have not set it up. I don't think so. I don't think so, honestly. But no, I don't think so. Well, what is Linux? This is the political question, right? Some people tend to, when we talk about Linux, some people could differ in what Linux means. Some of them are thinking about a whole distribution, a whole operating system, including all the package and everything. And some of them are going to tell you that that is GNU Linux, and Linux by itself is the kernel. We are not to be trying to clarify that question. Probably I'm going to talk about the kernel as Linux or as a kernel Linux. I don't care. That is something that I think is not important. There are because if Linux is the distribution, then we can think in Ubuntu, Red Hat, and Linux. I work in this. I work in this. But what about Yocto or Buildroot? They don't have formal. They are not formal distributions. They are just tools to build your own system. Then are they not Linux, or what happened with them? Or Open WRT that is running in routers. It is not a general purpose, but it is also a Linux distribution. Anyway, okay. Buildroot. What is Buildroot? Yeah. Buildroot is basically something similar to Yocto, but it's made of makefiles. Have you used Yocto? Yeah, Yocto used to use bitbake and all the recipes and classes. Buildroot is using makefiles and variables. It's pretty interesting. Yeah, it's another building tool. It's pretty interesting, mainly if you want to do something fast, because I think Yocto is awesome, but it has a learning curve, a really large learning curve. If you are starting, probably you are going to take some time to be comfortable with it. However, Buildroot, you can do something probably in a couple of hours. And I actually, the contribution that I did, everything that I was testing in Buildroot, because I just replaced the kernel in the package. And that was faster than being configuring everything. Well, when we talk about Linux, there are some simple things that we have to keep in mind. Linux is basically this. Okay, probably omitting this layer because this layer is the hardware, but yeah, Linux is user space application. You can name it whatever you want, the init process, and whatever init process you want, system B, system D, anything. A kernel, and you can even omit the bootloader. I don't know if you know, but there are ways to configure the kernel to have the kernel parameters, and you can put the kernel just exactly in the boot address of the device, and the device is going to boot your Linux with the kernel parameter that you choose. Yeah, it is interesting, but this is basically the thing that is Linux. It's as simple as that. But internally, Linux is a bit more complex. Linux have internally a variety of subsystems that help it to work properly. And in this case, with Linux, we are talking about the kernel. But anyway, probably you have seen an image like this before. And this is the common, from up to down, this is the common way how things happen in Linux. Commonly, you are going to be a big gatekeeper that is the system call interface, and everything in Linux is going to pass over that layer. What does it mean? That everything that you are doing in your computer, open a file, running a service, anything is going to be passing over that system call interface. And that system call interface is going to redistribute the work to any of the other subsystems. They could, if you are probably checking for a file, you are going to check first for the virtual file subsystem, and if the file is in the disk, the virtual file subsystem is going to down until the device drivers, and it's going to write physically in the device driver. And if you are, but if you are running probably in you are writing a file in a network file system, then the virtual file system is going to redirect you to the network interface. Not exactly like that, because it is going to go to the user space again and things like that. But anyway, you are going to go to the network interface, and you are going to send packages over the network. And when you send those packages, somebody else in the network is going to write it in the disk. Basically, Linux started with the mindset of Unix. Unix have two known rules. The one is that everything is a file. You know, everything is a file. That is why we need a virtual file subsystem. And the second one is the program should do one thing, and they should do it right. That is what there are some controversies with systemd, but we are not going to talk about that. Well, let me see. Make an interface. Okay, yeah, that's right. Now,
can you please elaborate a little more on the IPC concept?
Yeah, the IPC is a subsystem that allows the interprocess communication exist. It means that you could say, okay, but the IPC could be part of the virtual file system, and that is in part right and in part not. Because if you are doing name pipes, you are going to have a virtual file system not existing. But there are some times that you are not going to be working like that. For example, if you are using shared memory, you are going to be talking to the IPC subsystem, and the IPC subsystem is going to be sharing your information between the processes among the process management. Basically, is the subsystem that helps you to share information between your processes. Memory management is just providing you memory. It could be real memory, or even now there are things like CXL that allow you to have a memory from PCI devices. You can request memory that your graphic card is not using, and you can tell it, okay, PCI, I want that memory because it's not being used, and it is going to provide it to you, and you are going to be able to use it through the memory management subsystem. Okay, is there a question? I think there's a lot of them. There are a lot of them, but basically that is the context. We are going to be playing with this stuff. Probably a question is, what is the difference between the kernel and the user space? And the real difference is in the processor, because processors have some protections for memory, and for memory on data and in code, and some stages of processing that allow you to do things with the registers. In x86, they are called rings. I think in ARM they are called rings too. But what comes to my mind always when I say rings is x86, because they had 4, and we just use the first one and the last one. The last one we use it for user, and the first one we're using it, the 0 we're using it for kernel, and the last one for user space. And the other 2 was supposed to be for device drivers, but they are not being used anyway. And then depending on the mode that you are running in your processor, you are on user space or kernel space. But it also means that if you are that you have to flag your memory. If you also with these rings, some parts of your memory are going to be flagged as user space, and some parts of your memory are going to be flagged as kernel space. I said it right? Okay, user space and kernel space. Then if you are trying to access things more privileged, like things on kernel space being in user space, you are going to get a seg file. Actually, it's the seg file by itself is a processor interrupt, interrupt that is in hardware, and you don't you are not seeing the processor crashing because it has a trap that all those is doing a lot of fancy stuff to avoid it. But anyway, sorry, I got lost. Yeah, questions? No? Okay. Well, then we are going to the topic, right? Okay, basically, this is pretty simple. This is the configuration that I made for the thing that we are working. I'm using a resistor, if somebody was asking, and I'm using that mainly because I don't care about the brightness.
We had a whole meeting about
about LEDs and things like that. Yeah.
Slides are online.
Yeah. Then I don't care about brightness. I know I could use something with less resistance, but I just want to show the pin blinking. Okay, and this port that we saw in the past slides, I don't know, probably I can go there, is equivalent to this one that is ground, and we are using this other pin that is a GPIO port. And we are going to get the 3.3 volts from here. I forgot to say about the current. I remember that I have something about that. Just let me see where it was. I think, yeah, I think it is from 2 to 16 milliamperes for the GPIO ports. Well, just because I'm pretty sure that Frank is going to ask at some time. Okay, for those who probably would be interesting, I use a software called FreeSync to provide that image. It's a pretty good software that helps you to make some simulation and things like that. And I think it's open source. I saw the source code in GitHub, but I don't know. FreeSync. FreeSync with T. Yeah.
Sounds German.
Yeah, it is German actually. Yeah.
It's for free or it's free download? Yeah.
Yeah, it's free download. You can pay if you want, actually. Yeah, but you know.
Pay if you want. You get a better version.
I pay. I like to contribute to the, yeah, I like to contribute to this kind of project because, yeah, okay. Well, this is the question, right? How can we use the GPIO pins on a Linux machine? Well, the Linux is exposing GPIO to user space using the GPIO subsystem, right? Since the version 4.8, they are providing it with something that is called, like, as far as I remember, it's called GPIO aggregator, and this is exposing some character devices that commonly you can see them with the name of GPIO chip, GPIO chip 0, GPIO chip 1, and all the things that you need to perform over a GPIO, you can do it over it. You can request for a GPIO pin and send the pin as high, set the pin as low, change the mode of the pin, and sorry, I was not talking to the microphone. Yeah, and so on. Yeah, but how does it work? Yeah, also you can get the whole pins that are being in this GPIO chip. Actually, I had a problem with Raspberry Pi 5 just to, actually, I take income today because I wanted to use Raspberry Pi for this talk, and the weekend I changed all the slides, and I said, I can write the code the Sunday on the night, and I wrote the code for Raspberry Pi 5 the Sunday on the night. I compiled it yesterday, and I find out that it was not working. And I took 2 work days to try to fix it. And at the end of the day, I decided to move again to Raspberry Pi 3. The main reason was that Raspberry Pi 5 has 5 GPIO chips. And then for the purposes of this talk, we are using some legacy functions in order to be on the track of improving the code. But the thing is that that function doesn't work if you have more GPIO chips. And I didn't think in account of that until like 4 hours ago. Anyway, just let me take this because probably we are going to use it soon.
Could you possibly explain what this /dev means?
/devs are is a temporal file system. Actually, everything that is in /dev, everything that is in the /dev folder, in the /sys folder, /proc, and /run, also in /temp, all of this doesn't exist. They are not real files. They are files that lives in memory. That is why when I mentioned about the virtual file system, I mentioned that if the file is in a disk, it is going to go to the device driver. But if not, it is going to just show you a file that is not existing. But it's a point of communication with your driver. In this case, it is a character device driver because you can write to it streams of bytes. There are all kind of device drivers. But sorry, I remember that I have this one. Okay, just give me a second. I'm going to put this here. We are not going to use it right now, but I want to be prepared.
The 4.8 is the more stable version?
No, right now we are in the 6.9 in release candidate, as far as I remember. Then just think, from 4 to 6.9, there are lots of versions. Actually, but this change came with that version. That is what I am mentioning, because in the case of embedded devices, you can have devices that are not updated because they probably don't have network or something like that. Then it's important to know in what version something changed. Actually, I have experiments and things like that, but we are going to talk about that soon. Yeah, some problems with that.
So the 4 is the kernel version?
Yeah?
4.8 is the kernel version, right? Oh.
What? Which one?
4.8 is that the kernel version?
Yeah, it is the kernel version, actually. The most known version, as far as I remember, at least in my young, was the 2.6, I remember. Yeah, some years ago from that. But yeah, anyway. Yeah, the GPIO subsystem have a user application interface. That is what UAP means. If you explore the Linux kernel source, you are going to be in the include section, something called UAP, is user application interface. That is all the headers that the kernel is sharing with the user space and could be used to work with it. Then all the devices that we mentioned before are used commonly in C to communicate using I/O control calls. But we are going to talk about this soon. But they are also, it is also used to create bindings. And one of the popular bindings is this GPIO 0 in Python. Commonly, if you Google how to communicate with GPIO using a Raspberry Pi, you are going to see this. And believe me, you are going to see lots of this. And probably it's going to be a bit hard to know how to communicate because Raspberry Pi have the strength that is too popular, but as it is too popular, people does not go deeper. But well, in Python with GPIO 0, you can perform some GPIO tasks pretty easy and pretty fast. They have these base classes that are going to, once you instantiate one of these classes, you are going to set up the GPIO pin in one of these modes, output or input. And also, if you want something more specific, you have some subclasses that are for particular purposes. It means that in terms of code, these two versions of code are practically the same. This is just doing a blinking, but internally, this is doing practically that. Yeah? We are going to go deeper. But if you want, we can try this. Just let me.
Is there a difference
Uh, you are in Python. I don't think you care really about the about that. Mainly because give me a second. Probably I don't know.
¿Qué necesitas?
Yeah, this one.
Se va a desconectar el...
No problema. Para conectarlo aquí, pero primero lo conecto después y creo que no tengo teclado.
¿Es un teclado?
¿Tienes un teclado? USB, por favor. Perdón. No pensé en eso, según yo revisé todo lo que tenía que hacer. Vamos a probar esto. Esto es algo que quiero que hagamos. Vamos a tocar un tema, vamos a explorarlo y después vamos a ver cómo funciona en realidad, ¿verdad? Porque, no sé, me siento más familiar, más cómodo con eso. Creo que no tenemos teclado. Lo siento, según yo sí había traído teclado. Tengo es un Raspbian, no es nada fancy, no crean que es un Gentoo ni nada. Es un Raspbian, pero instalé la versión mínima, porque no quiero interfaz gráfica. No la voy a ver de todas maneras. No, esa es toda la información.
A ver, creo que segundos, sí.
Ok, gracias, y disculpa, debí de haber pensado en esto antes. Bueno, a ver, nomás que está en español, no sé cómo va la configuración de Débora para eso. A ver, Josue, DHG. Este era.
The power of failure to start Raspberry Pi Bluetooth helper is because the signal is missing.
Which part?
The faded Raspberry Pi Bluetooth helper.
Yeah, probably. I don't move nothing about that. Then I don't care. That's not my problem. Okay, I missed the password. What is? No, según yo sí era ese. Perdón. Josue. Now, sorry. Actually, as far as I know, that was the password that I used.
No password.
A ver. No. Yeah, sorry.
El idioma del teclado es compatible con password.
No creo, es que tengo Débora en inglés.
The default one is Pi, first one? Pi and Raspberry.
It is the 5, right? Yeah, this is the 5. Actually, it has a Linux loaded, but it is the device driver, the kernel modules cannot be loaded because the kernel is tainted.
The default is Pi and Raspberry.
Pine?
Pi.
Okay. Pi.
And then Raspberry. R-A-S-P.
Okay.
B-E-R.
Pi? Sorry. Raspberry. No. A ver. Okay, it's okay. Pi. Raspberry. Nah. Okay. We can try this at the end. Sorry. ¿La otra qué? No. Esta es una 5. Esta es una 3. Digo, tuve ese problema con la 5, entonces me cambié, regresé a la 3. Pero si no, ahorita al final lo podemos jugar con eso. It depends. No, I don't think so, because you need to have access to the GPIO ports.
¿Quieres poner para que no te estorbe?
No, estoy bien. Yeah, the thing is that you need to have access to the GPIO ports, then you cannot virtualize the GPIO ports. There are tools, but I think they are going to be pretty slow. Well, anyway, basically what this was doing was just blinking the LED. Actually, I don't have the LED. Anyway, well, the custom kernel version. Now we are going to go into the kernel. Actually, let me talk a bit more about this. What is the problem with this, actually? What do you think that is going to be the problem with this? Other that is not the performance, because we are running basically an interpreter and things like that. But the problem, the first problem is in the perspective of software engineering, is that your software is aware of what your hardware is, right? It means that if something changes in your hardware, or you want to run this program in another place, you are going to need to change every part of your software that is doing this. Probably this could be solved just isolating the part that is communicated with the GPIO, probably a service. We can have a service that is communicating with all the software that wants to have something like GPIO communication. But and we can do it in user space. Okay, it could work, but we already have a way to do it, and it's the kernel space, right? Well, we are going to start to talk about how to create a custom kernel driver. And the first thing that we have to have is obviously a computer with Linux or something similar. And we are going to need the kernel headers of the target device. If we are creating device drivers or kernel modules for our host machine, then we are not going to need a cross compiler. But if we are going to be working for an external device, that is our case, we are going to need some cross-compiling tools. What is a cross-compiler? That could be a question. Okay, first of all, everyone knows what a compiler is, right? Okay, well, okay, sorry. Okay, first, I think everyone knows what a compiler is. Then what is a cross-compiler? A cross-compiler is a compiler that is actually a binary in the architecture of your host machine, but it is going to be producing a binary in other architecture. In our case, in our case, we are going to be using the ARM Linux. I remember the last one. Okay, it is producing code in ARM, and for that one, for the Raspberry Pi 5, I was using an AArch64, that is the compiler that is going to produce code for ARM64. You can do it in this way, mainly because if you try to compile the whole kernel in your Raspberry Pi, it is going to take a while, really. Mainly in this one, because this one have just 1 giga of RAM. Then, actually, I didn't do this in this computer. I compiled my kernel and everything in my home computer which have 32 gigabytes of RAM, and yeah, it's a big computer. And just because I don't want to be trying and waiting 1 hour to have the kernel, but anyway, That is a cross compiler. If you are running in this way, you are going to need one. If you want to try to do it inside your board, it's okay. It's your time.
It will be slower if you do it virtualized.
Yeah, because when you virtualize a system, you are going to assign just a fraction of your memory. If you are virtualizing a Raspberry Pi 3, you are just using 1 gigabyte of RAM. Then, even if your system is bigger, you are not going to be compromising the rest of the RAM. Well, when we think in develop a kernel driver, there are something that we need to think. The first part is the non-coding work. What does it mean? The pre one is funny, how our device driver is going to be named. But yeah, some people see this as a really important thing, mainly companies and things like that. But the second one, in my opinion, is the most important. It is what is going to be the protocol that we are going to be using to communicate with the driver. This is called in Linux as ABI, an application binary interface. It is the interface that is going to be using between the user space and the kernel space. And in our case, we decided that we are going to just be passing a 1 to the device driver, and with this we are going to turn on the LED, and when we pass a 0, we are going to turn it off. Pretty simple, but just think there are protocols as complex as the word, because you can have a protocol over SPI, like, I don't know, I was thinking in the book protocol that is called Sneak Peek, or this other one that is used for the FTDI to program things. Anyway, you can use different protocols, and some of them are already defined in the kernel, some of them not. And the next thing that we have to consider is the coding work, because with the difference of the last part, we are going to coding a little bit more. The first thing of coding is we have to see a way to create a way to communicate with the kernel. It is the character device driver that we are going to be using. We have to make it visible. We have to have the ability to write to it, and the way to know the status of it. It means read from it. And once we have this, that this is just the part of the communication with the kernel, we are going to be thinking on this. Because if we are not able to communicate with the kernel, there's no reason to communicate with GPIO. Well, first things first. What are the starting points for the kernel module? When we are writing a kernel module, the entry points to use are actually called init module and clean module. But these macros of here are changing and creating an alias with the compiler to be pointing to these functions, to the function that we choose. This is a trick of the kernel, of course, and these are macros. Just at the end of the day, the symbol that we are going to be seeing is going to be this one, but every time that we are going to, but we are going to be seeing also the other symbols. For loadable kernel modules, we commonly use this init and exit. There are just macros that, I don't know if somebody of you have used the section preprocessor macros, the section preprocessor macros. These macros help you to manipulate the compiler to do special things, actually the linker to do special things. And this, what they're doing is just put the code of these functions in a special section that is going to be deleted at some point. And that is why it's important to have them, because if you don't put these macros, your functions are going to be living for the rest of the existence of your execution until you turn off the computer. Okay, let's see. Okay, I already talked about this. Okay, basically, if you are doing a tutorial of how to create a kernel module, you are going to see these two functions. Probably not with that name, but this one, but with that signature, actually. Actually, I need the word, but anyway, because I also have the code there. Well, the next thing that we are going to do when we are creating a kernel module, or in our case, a character device driver, we are going to see this function, these 4 functions. The first function is going to just say the kernel that we are going to need some special numbers that are called major number and minor number. But what those numbers means? Have you ever do an ls over /dev? Yeah? If you do an ls minus L over every part of your file system, you are going to see a section where the size of your folder is. But if you are doing it over the /dev, you are going to see 2 numbers there. And those numbers are major and minor number. But okay, what are the meaning of those numbers, right? The major number is as simple as this. Is an identifier of what driver is going to be executed when you write or when you perform a file operation over that file. And that is the major number. It's basically an identifier. And the second one is it will depend on the driver implementation. For some implementation, or for the majority of it, it is an identifier of the device. For example, if you have 2 hard disks that are exactly the same hard disk, but they are 2, you are going to see a 0 on one and 0 in the other. Okay. If we achieve to turn it on, we are going to see the whole code there. So I promise. If not, I'm going to send it to you a GitHub link with all the code. Actually, I don't push it to the GitHub. But anyway, that is the first one. It's just allocating the major and minor number. The second one is going to initialize a character device. Actually, it's a class. No, it's a character device. It is going to initialize the character device. For this, we are going to need a special struct that is called file operation. This struct is going to have function pointers. Have you ever think about, or have you ever seen how to implement an interface in C? You know, interfaces like in oriented object programming. This is the way. It's basically the way to implement them. It's just a struct with 5 pointers, and all the 5 pointers are for what is going to happen with every file operator. What is going to happen when the file is opening, when the file is closed, when you read from the file, when you write from the file, and so on. And the second part is just the thing that is going to be allocating this one. When you initialize it, you are going to need to add. This part is going to inform the kernel that there is a character device driver in the system. It's not just add for add. Once you do this, you have a character device driver. But you cannot see it. You will need to perform things like mk node, create a new node in order to see it. Anyway, Uh,
So this file operations is a record of functions, right?
what do you mean?
I remember vaguely, I looked at kernels at once, but this is a struct which contains function pointers.
Yeah.
What are the possible things you can do
Yeah.
with the device?
Yeah, it contains function pointers. I mentioned just a couple of them. Open, close, write, read, write, and IO control that are special functions. But you don't need to implement all of them. You just need to implement the function that you are going to be using. The rest of them could be pointing to null, and the operating system is going to ignore them.
So this is functional programming, way before Kotlin was cool. So people actually used to do this stuff. I mean, it's not a new idea, and it's so ingrained in this world.
I would say that it's more oriented object programming, mainly because all the concepts that the kernel have actually are based on oriented object programming. One time, Linus Torvalds said that he wanted to. There was a time when they wanted to move the kernel to C++, but it did not work.
Linus didn't like that, no?
No, Linus didn't like it, but they wanted. But there are some concepts like the kernel object or inheritance that are happening inside the kernel. You know how inheritance is in C? It would be great if we have this was not in the topic, but it would be great if we have something to write just to mention it. But anyway, I got lost. If you want to show with the last part, oh sorry, this is one of this. With this, you are going to tell the kernel that your device is ready, but you are not going to be able to see it. You need to create a new node to see it. There are some ways to do it automatically. There is a thing called UDEP that is reading kernel events or is exploring /c, that is a way to communicate with the kernel, just to see when something happening to react. You can create one, but that is not the way to do it. This is the actual way to do it. You can create a class. It is more like just creating the device, but these functions are going to create your device in /dep. Basically, what they are doing is create a type of device. If we are going to be working with the LED, we are going to use the first one to create our type of class that is going to be LED or my LED. And then we are going to create a device that is going to belong to that class. Yeah, this is the second function, but it is really large. Basically, when we perform this device create, the kernel is going to trigger a kernel event that is going to be read by UDEP and by a rule that already exists, and that is going to be creating the device. Yeah, with this, basically we have the creation of the interface of the mechanism to communicate with the user space. But we mentioned before that kernel space and user space are flagged differently. Then if you are trying to read something from kernel space, you are going to get a seg file. Then how they share information, because at the end of the day, we are going to be sending a one to our device, and the device is going to be getting that one, and we are going to respond when they wanted to know the status. For that, we have these functions. Internally is really complex because they are practically locking the memory address, the memory section, to be able to use it without problems. But the better way to do it is just this, because if you are trying to do it in the other way, manually, you can experiment some unexpected behavior, mainly because the application could go out of the processor, and when they do that, it is going to free all the memory, and you are going to be writing to a memory that doesn't belong to any process. Then these mechanisms are the way to do it. You can copy information from the user, and you can write information to the user. And with the user, we are talking about an address on user space. In this case, everyone that has this flag is, everything that have this flag are addressed from user space. You can write practically everything. But, okay. Well, with this, we know how to create the device driver, how to write and read from it. And this function, I think, could not looks pretty unfamiliar for every one of you. If you have played with GPIO, practically they are the same in every device, just with small differences. In our case, we are requesting the GPIO and getting a descriptor after it. I'm going to explain this soon. And we are setting the direction of our device. In this case, we are going to be using this output function, and we are going to set the default value for that. And finally, the functions to set and get information from the pin. Why we are getting this function, this descriptor? Mainly because the GPIO structure right now in the kernel is more complex. Then this function is actually being deprecated, but if we are going to do a simple driver without going into complications, we will need to use it. Actually, this function was the one that I was not able to use in the 5. And anyway, well, this is the moment when I wanted to show you the code. Okay, but basically, with all this information, we would be able to build something like this. In the user space, we are going to see a character device driver. This is going to be our driver, the thing that we are going to be writing. Then this character driver is going to write to the GPIO driver using the GPIO lib. That are the functions that we saw a moment ago. And finally, the GPIO lib is going to be handling the LED. I don't know. Let me see if I can just. Yeah. Let me try it again. If I got an IP, it would be great. Mainly because I can just. Actually, do we have Ethernet? No, but I would not know what the IP is. What?
That's the keyboard.
Well, okay, yeah, got it. Actually, let's see. Woo! We have it! Great. Okay. Let's. Yeah. Let's do it the full setup. It is not really complicated.
Put it on a sticker and put it on the board.
I just turn on the block gnomes and it works. Yeah. I don't know. Let's see. Okay. Yeah, it would be great. I use this for ground and this for.
Color doesn't matter, right?
Yeah.
left.
Is the Raspberry Pi damaged? Is a software failure or a hardware failure?
Sorry, could you repeat that?
You say the Raspberry Pi was damaged. Is because this software damaged it or?
No, actually the problem.
¿Puedes repetir la pregunta que está haciendo para que se escuchen en la transmisión?
He is asking me why I said that the Raspberry Pi was damaged. But actually, the Raspberry Pi is not the thing that is damaged, it's the kernel. The kernel is tainted. This happened when your kernel is not trustable enough to be executed. In this case, the main reason was that I was loading a module that was not in accordance with what the board had. I mentioned this before. This Raspberry Pi 5 have 5 GPIO chips, and the GPIO chip that I was looking for was the 5th. Then I was not able to reach it with the simple functions. I know there is a way, but I find out what was happening just some hours ago. Then then I rolled back everything that I was doing. I wanted to do it with the Raspberry Pi 5 because I bought it last week. Then then I said, okay, it would be great. But anyway, let's sorry. Ground is to the third pin. Yeah, this one. And current is to the last one.
The last one,
Yeah, that one. Okay.
And I hope that's the right resistor. Check the.
Yeah, it's the only one that was there.
There's another one.
No, there is
It's a lower
no.
one.
Actually, it is not the right one. I
Okay.
remember the colors. Let's see. It was
It was that one, right?
yeah.
That looked
is
very
this
low.
one.
So.
Yeah, I remember the colors. Okay, sorry. Okay, let's see first. LS, RSP, GPIO, LS. I think probably the colors are not good. Okay, so GPIO, BIM. Okay, don't worry.
It should work.
Oh, what happened? Okay. Ah, it got restarted. No. Okay. 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 We are going to start. I don't know if we can have this a little more.
I can hold it.
Okay.
Well, last time I did this.
Okay.
I'll try and hold it.
Okay. Oh. I don't know if I'm writing. I'm writing or I'm not writing. Okay. No, these are not the numbers. Come on. Come on. Oh.
Oh no.
Sorry. There it is. Great. Okay, then CD, first S, and the first one is GPIO 0, and we are going to run GPIO. Okay, blink. Blinking dot py. This is the first one. Yeah. Come on, not phone. No, actually no. Let's see. No. The slash. Oh, it's because the keyboard.
Almost. Almost.
This one.
Yes. I just try tapping, maybe that works.
Blinking. That's fine. What? Yeah, running as root. Sudo. Look. This is a simple. Yeah, this is a simple one. This is the Python version. This is just the. Yeah, this is the one. Actually, it is not very fancy because if I interrupt it, it is. But I have a second version. What? Why is not writing that too? Okay. I have the second version that was the one that was in the other side. It is not optimized, but it is working.
Is it blinking?
Yeah, it is blinking. Yeah, this is the simple version. Well, now we are going to the kernel, right? For that. Sorry, I was preparing. Okay, I already compiled it, but I want to show you the code because I did not compile it in this. I don't have the headers here. Yeah. What we see is okay. It is okay. In the top there are just includes. Don't worry about them. But basically, check as we were talking. Probably you are going to see some of this function a bit familiar. The interesting thing are these two functions, read and write. They are using the GPIO get value to get the value from the pin, and it is using copy to user to write to the user space. And in the case of the write, we are using copy from user to get information from the where is the cursor? Is there? Here it is. There it is. From the user space, and depending on of what we are getting, we are setting the pin. This is the file operation that we mentioned. We just have to mention what is the owner. In this case, this is a macro that have an identifier for this module. And the read and write function are the function that we see above. This is the initialization function with all the information all the functions that we mentioned. The allocation of the major and minors, and so on. These are macros to check if everything is right. Are macros from the kernel, but they are not important. You practically could use an equal, and it's practically the same. Just it's common to use them in case they decide to change how they work. We have some, as is usual in C, we have to free everything if something is wrong. And also when the file, this is the exit function, then we want to liberate the GPIO and all the resources once the kernel module is unloaded.
So C has gotos.
Yeah, C has gotos. It is not too common to use them, and some people are against them, but they are practical. Actually, if the language have them, some people doesn't like them mainly because in C you can jump out of the function. That is something weird. Then you can make a mess with your stack. But if you're using in a measured way, it's okay. Okay. Well,
yeah.
here is.
David has a question.
Yeah.
The Python before was using a library, not using this driver.
That is exposing the GPIO chip interface. In this way, we are creating a LED driver. Then this LED driver is exposing an interface to turn on and turn off and turn on the LED. But we are talking directly to the LED through the character device drivers. Internally, we are using the same. We are doing practically the same that the Python one.
Should we see something in slash there?
Yeah, that's the thing. Let's see. We are going to sudo insmod mylet.ko.
KO, I think it's kernel object.
Operation not permitted? What? Let me see. Yeah, it's kernel object. lsmod. Probably, damn it. Probably I have something already loaded. Where is the pipe? Sorry.
You don't need to bring your own keyboard.
Okay. Give me a second. And there is a Raspberry config. Raspberry minus config command as root sudo. Okay, let's see, just to change the keyword. It is going to 55. It is 55, I don't know, but other, I think, is Spanish, Latin America, I don't know. I don't used to use Spanish keywords. I'm going to use this one. Let's see. Spanish, Latin America, this one. Yeah, the right hand. Okay. Sorry, but I probably should have my own keyword. Well, what I was seeing was ls mode. Now the problem is that I used to write in the work, but I kind of remember this. Where is the pipe here? Is what? Where's the pipe here? Ah, the pipe. Grab my left. Yeah, my left. Ah, there is no driver. Then what is happening? Sorry. No, I don't think so. Insmod sudo. Let's see the message. The message. No, there is no problem. If there was a problem, the problem was at the end, and we have all this Bluetooth thing. I don't know. Let's continue. I'm just let me check it. What happened? Info. More info. Anyway, let's continue. I'm still doing this, right? Everything looks. Yeah, but I think is the the right one. 6.1. Actually, I built it, and the architecture is also the right one. Anyway, let's continue. Yeah, at least I'm not able to show you the code. I don't know. Let's see. I'm just seeing if everything was properly configured. And I don't think that was the problem. Anyway, now we are able to do this, but we have now this question. Okay, but there is a saying in engineering that if something is working, don't touch it or something like that. I'm pretty sure that you have heard about it, but that's not okay, right? Because things could be working and could be wrong. And what is wrong with this? Now that we are talking about kernel driver, there are two things that are wrong here. This is not the keyword. And this is that we are exposing this device driver with our own ABI. That is not okay. Mainly because probably if you are doing something particular for you or for your company, it could be okay. But in kernel terms, you are not using the real kernel. I know what is wrong. Yeah. Anyway, no. You are not using the real kernel. You are not taking advantage of the kernel functionalities. I mean, in the case of the LED device driver, we are just blinking it. But what happens if I want that the LED is turning on with the hard disk consumption, or if I wanted to be tracking the CPU bit hertz? Should I write an entire driver every time that I'm going to do that? And this kind of thing happen if we decided to go over our own ABIs. I mean, there are tools in the code to do it, to say this kind of LED driver is going to be working now with this trigger. They call them trigger. That is just one part of the problem. I am saying too much. We are going to go over there soon. But the other problem is also that our character device driver also knows too much about the kernel device driver. It has to know too much about the hardware, right? Actually not. We are going to talk about how to avoid that and how to improve our kernel with some tools. We are going to talk about LED class drivers. In the kernel, there is a part of the kernel that is called the input section. There are a consumption of kernel subsystems that expose functionalities to be used. And one of them is the LED class driver. You have a complete LED interface, LED subsystem to work with it. And not just for blinking a LED, you can also work with RGB LEDs and things like that. And also LEDs that are in a device that is. But with this LED class, we are going to avoid a couple of things. The first thing that we are going to avoid creating our own protocol, an ABI. We are going to be using the LED class driver ABI that already exists. And the second thing that we are going to avoid is creating all the functionality that is going to be used to expose the device driver, because that LED class driver already have one. For the GPIO, we are going to need to still be working on that. Well, for the LED class driver, we need to use these functions. The first thing that we will need is create an struct with just these two properties. The first property is going to be the name that we are going to display for our LED. And the second one is going to be a callback. that is going to be called every time that the state of is going to inform us when somebody is changing the state of the LED. And this is basically the signature of the function that we are going to be using in the callback. They are going to be passing the LED class device structure to us, and an enum that is going to have the information about the state of the LED. It could be low or high. Finally, we just need to register our LED in the LED subsystem, and it is going to be working. But with this, what I want to say is that this kind of frameworks that are provided by the subsystem, there are lots of these frameworks that are provided by the subsystem, not just for this. There are some of them for input devices. What happens if you are going to need to write the whole driver? No, you can use a framework that is taking advantage of a subsystem. For many other things, like, for example, the GPIO, DRM, that is the part in charge of managing displays, or things like that, you don't have to write it. You can take advantage of what already exists. This is not the keyword. If we think of this, sure now, the exposed interface is not going to be in this class LEDs. LEDs is the class. And this is the name that we choose. It is a standard for names that not all the people is following, but commonly the first part is the name by itself. The second one is the LED color, and the third part is the functionality. I put user because this is a LED that is going to be controlled by the user. We are going to have the LED framework handling all the creation of this character and the reading from it. Our code is going to be here, and the rest is going to... Can we go over the device to show the code?
We might have to wrap up soon.
Okay. Sorry.
It's fine. How much more do you have?
Okay, if you want, let me continue. If somebody wants, yeah, we can do the demo. But I have another one demo.
Okay, then let's do that and skip the second.
Yeah, we can continue and at the end show the code. Okay, well, sorry. Well, but with this structure, there is still something wrong that we already mentioned. That was that our character device driver is now into the hardware. But how can we fix this? To fix this, we have to talk a bit about buses. The kernel has something called the kernel bus infrastructure. And this kernel bus infrastructure have 4 main components. The first one is the core that is an API that is going that is basically the implementation of the bus. The second one are adapters, drivers to be handling the bus. And the bus drivers are the driver devices, the representation of the devices in the bus. Well, in the kernel, everything could be connected to a bus. But we can think that if we have a LED connected to a GPIO device, it is not a bus by itself. The kernel uses its capability to create virtual things, and they create a virtual bus that is called platform bus. Okay, this is not the keyword. And for this platform bus, we can register our driver in the platform bus, and the bus is going to inform us when the device is connected and when the device is available. And register it. The first function is going to looking for this string in the devices. And the second part is the representation of the driver with the callbacks to prove and remove when the driver is loaded and when it is removed. Basically, we are going to change our init my LED driver init for this other signature, and or my LED driver exit for this other signature. And we are going to need to get information from the bus in order to know what GPIO number is connected, and the label. This one is to get actually the label that we are going to assign to the GPIO. The GPIO device. Okay, with all this, we are going to have now these structures. One, we are going to register our device in the platform bus, and the platform bus is going to inform us when the device is going to be loaded, and also when it needs to be removed. It looks awesome. And it looks like there is nothing wrong. The other one is the auto-discovered. Some buses like USB and PCI, and I think I3C, the improved I2C version, are auto-discoverable. They have an enumeration process that allows us to know when an additional hardware is connected. And the last one, that is the important one, is the device tree structure. In the case of embedded devices, we don't have these other mechanisms, with the exception of some ARM64 devices. There are some boards that actually have ACPI. I have not seen them, but I read about them. But anyway, then we have this blob are created with sources that are called device tree sources. Then what was missing is that. How can
That's why it's so many troubles with the connection of drivers in Linux and outside devices.
But it could be. I don't have too much problems with Linux, other than this. But okay, what is a device driver? I already mentioned this. Sorry, I'm trying to go fast. And yeah, the sources are commonly compiled by a device tree compiler, and they produce device tree binaries that they have the information of device tree blobs. I think they are called. In the Linux kernel source code, we have all these device tree information in this folder. The arch it could be replaced with the architecture that we are working on, but it just works with the platforms that already have this mechanism, because in the case of x86, they doesn't. And you can compile them with this command. Actually, I'm using cross compilation for this. And this is how it looks for the board that we are working on to get a LED to inform for. This could be named as you want, but the important thing is this one, because we are going to inform that we are working on a GPIO device. This is pointing to another part of the device tree source that is describing the GPIO chip 1, and we are requesting the 21 from one GPIO port to another. We won't need to compile the whole kernel or compile even our kernel module. We just need to create another device tree and load it. And this is the final structure that we are going to get. The device tree is going to inform the platform bus that a device exists. The platform bus is going to run our driver, and our driver is going to be exposing the LED. But in order to be honest, all the things that we have been doing is just for educational purposes. because we can do exactly the same just doing this. If we add this code to our device tree, it automatically is going to run an already existing driver in the kernel to expose. This is a problem that kernel developers have faced so many times. Then they already have a driver for that, for a GPIO LED. And that's it. This is basically the references that I consulted to perform this talk. Yeah, references. Sorry.
First, thank you very much for a very interesting talk. With a tour de force going through the kernel implementation, character devices, platforms. So I think it's very comprehensive introduction to this and see how all this works. So any questions?
You said we can use Raspberry for setting up a Kubernetes cluster. Is it way more efficient than cloud machine?
Okay, are you talking about Kubernetes?
Yep.
Okay. I don't know, honestly, I don't work with that. I know Kubernetes and I have performed a couple of things with that, but honestly, I don't know. That is not the kind of thing that I do. No question? No? Actually, what was wrong now that we were working with the driver is that I was testing this part of the code in the machine. Then I had this the binary, so the device tree binary because there is already a driver that is requesting that GPIO. That was why nothing was loading any of my kernel modules, but I can change it and work with it without problem. Yeah. Sorry.
Any more questions?
The project is already in your GitHub repository?
The project is already in GitHub repository?
Not right now, but I'm going to upload it. Actually, it is in a GitHub repository, but it is local. I just have to perform a push, and it is going to be there.
Yeah. I think it would be great to put it into the GitHub, maybe the slides as well. So
Yeah.
if anyone wants to see it and try it out. It's very useful. It's not a lot of code, so it's very interesting to see how with a little bit of code you can do something quite amazing.
Yeah.
Like writing a device driver. So any more questions? So otherwise I would say let's thank Josue as well for doing such a great talk. And we have a bit more time, a bit of short of time now, so we have a short break, 10 minutes, and then I will do a very quick run through the second part of the social. And afterwards, if you fancy a beer, so help yourself to beers, these are all for you, if you like to. And if you like to have some food afterwards, you might go for some food at 10. So I quickly try and set up and tell you a bit more about the second part. And if you'd like to do a talk like Josue did, just contact me, contact the group. We're always very happy to have speakers to come talk about different parts of embedded. It doesn't even have to be super embedded. It could be something related to IoT and other things as well. Yeah. So 5 minutes. I'm going to continue. Thanks. Thanks very much for this. Very nice.
Sorry,
Don't worry about it. It's just we have kind of, you need to be a bit careful, I guess, at the time. We need to get out of attention.
Only a possible solution, I don't know, for the Raspberry.
Okay. Yeah. Actually, let me try to make it work.
For the Raspberry Pi, it could be that synchronizing the cycling, it would be different for the tree.
Perdón.
Ese cuesta